All right, folks, I really want to finish the problem we had to be in the same theme with a lecture. So we're going to do example number 2 on your chapter 23. So let's look at this for a moment. You have an electric dipole that is formed by a plus minus 1 nanocoulomb, right? So I represent them both cases here. And the charges are separated by a 2 millimeter apart. So the dipole is situated on the x-axis as represented in the pictures I just drew. And the question is, what is the electric field strength at the points? And in case A, they tell you it's on the x-axis, which means on the axis of the dipole. And part B, it's going to be on a bisecting plane, right, of the dipole at the same height or distance. So with that being said, because it's kind of going together with what we discussed in class, so let's look at this for a moment. If you look at the formulas that we learned today, right? So if you, and we actually derived, we have the dipole, the electric field created by the dipole on the same axis like the dipole, looked like this. Electrical field in there is K, so 1 over 4 pi epsilon naught times 2 times the dipole moment, P, divided by r cubed. All right, so this happens only if the dipole or I would say if the electric field is calculated on the direction of the dipole. As opposed to if you are calculating now the electric field on the bisecting plane, right, we get something like this. The electric field for this situation was negative 1 over 4 pi epsilon naught times P over r cubed, where r is the distance from the dipole to the point of interest, in our case P. So if you look at the problem and they ask you, hey, calculate this at x equal 10 centimeters, that means it's going to be on the axis of the dipole. We're going to continue with this. And here, for the y equals 10 centimeters, that means on a bisecting plane. They don't tell you this in a problem, but you got to recognize that. So what's missing out of this? Well, what's missing is, for each situation, if we find what the dipole moment is, then things are clear. So let's start by doing that first. And remember, principle of superposition, right? So at point P, right, the electric field is going outward, generated by the positive charge, represented here by the red vector. And from the negative charge, you're going to have an inward, represented here by the blue vector. And of course, you have to do principle of superposition. The E net would be in the direction of the larger vector if it's on the same axis. And in the case of point P being on the y-axis, so being perpendicular on a bisecting plane, well, then you have to actually draw a line between the charge and the point P and extend it out. Similarly, a line from the positive charge to the point of interest P and extend it out. And remember what it is. If you're dealing with a positive charge, then the electric field is going outward, hence represented here by the red vector E plus. And if it is, and it's in the direction, right, between the charge and the point P, it's on the same line. And if it's the negative charge, it's going inwards, represented here by the blue vector. And then you're going to get an E net. And you will see, because these are actually equal, you will have an E net parallel to the x-axis. Okay, so let's go ahead and calculate what is P, which is our dipole moment, right? And this is Q times so-called S, right? Where S is actually the separation distance. And the separation distance was given to us as being 2 millimeters. We're going to put here, this is your S. All right, so our P ends up being 1 times 10 to the negative 9 times 2 times 10 to the minus 3. And that's not being correctly 2.0 times 10 to the negative 12. All right, and this is coulomb meter as far as the units are concerned. Okay, so now that we have that squared away, let's look at the electric field on the first case, on case A. So in this case, and by the way, it's actually good to specify the direction. If I keep this as a vector, this was absolute value, but if I am to put this as a vector, right, I'm going to have 2 times 10 to the negative 12, and this is, this is in the direction I, right, in the x on Coulomb meter. Okay, so let's go to case A. I'm going to put an A here and a B respectively there, as this will apply to both of them, right? Let me move it a little bit down here. Okay, so what are we dealing with here? Well, we have E. Okay, so 9 times, or 8.99 times 10 to the 9. And what are those? Newton meter square over Coulomb square. All right, in our case, times 2. So we just copy the 2 from our formula there. And then we had 2.0 times 10 to the negative 12. Okay, so this is I hat, and this was Coulomb meters. All right, all divided by the separation there. The distance was R equal 10, and those are centimeters, so 10 times 10 to the minus 2, and it is cubed. And those are meter cubed in this case. All right, so by performing everything here and simplifying your units, let's see, so we have a Coulomb, and that goes away. You have a meter squared and a meter from here that goes away. That meter and that meter goes away. So you essentially, as you can see, you end up with Newton per Coulomb. And I am getting 36. Let's put that in there. And again, this is in the x-axis direction. That's why you put your I hat, and these are newtons per Coulomb. All right, so this was for case A. Now we're going to go back to case B. We already have the formula. I'm going to copy that below here so we have it. So we have E in this case, negative 1 over 4 pi epsilon naught P over R cubed. Okay, so negative 9 times 10 to the 9th. Put the units there, please. Newton meter squared over Coulomb squared. All right, times. Let's see. So we have 2.0 times 10 to the minus 12. This for Coulomb meter. Okay, and again, 10 centimeters. 10 times 10 to the minus 2. These are cubed. Put the units there, meter cubed. All right, and this was in I hat also. I'm gonna squeeze it in here. That means in the end, it will come in the x direction. And you can prove it geometrically based on a picture I just showed you above. All right, so let's see what we get here. We should get a half, actually, so of what we got before. Yes, I'm getting 18, so negative 18. We can put I hat, and then this is Newton per Coulomb. All right. So the field strength at this point is essentially 18, but the negative sign shows the direction, which shows you that it's oriented towards the negative axis, right? So towards the negative part of the x-axis. It is parallel and in the negative direction. All right, and that's it for this problem.